some meeting face to face with you.
Right.
Yeah. Okay.
Yeah. 4 of my students are stranded in China.
Okay. And later maybe she will transfer your WeChat to me, and then I will transfer to Professor Zhang.
Sure.
Yeah. Okay. Thank you. Professor, now you can start now. 伟业，开始了，刚刚开始。
Okay, good afternoon, everyone. I'm Professor Hua Zhang from City University of Hong Kong. Welcome to a series of virtual academic seminars to celebrate the launch of Smart Mat. Smart Mat is an open access journal co-launched by Valley and Tianjin University. I'm one of the co-editors-in-chief. The other co-editors-in-chief is Professor Wenping Hu from Tianjin University. This afternoon, Professor Michael Zaworotko will give the fourth seminar. Before his talk, let me briefly introduce Mike. Mike received his bachelor and PhD degrees from Imperial College in 1977 and the University of Alabama in 1982, respectively. He served as a faculty member at St. Mary's University, Nova Scotia, Canada from 1985 to 1998, at the University of Winnipeg, Canada from 1998 to 1999, and at the University of South Florida, United States from 1999 to 2013. In 2013, he joined the University of Limerick, Ireland, where he currently serves as a Barnard Chair of Crystal Engineering, Science Foundations of Ireland Research Professor, and co-director of the Synthesis and Solid State Pharmaceutical Center. He is a fellow of the Royal Society of Chemistry, the Land Society of Wales, and the Institute of Chemistry of Ireland. He is also a member of the Royal Irish Academy. Today, he is going to talk about why crystals will save the world, a story of GrACE, SALMA, and SAM. Mike, please. Mike, please, your turn.
Yes, I can't share my screen here. Let me try. Okay, there we go. So thank you very much, Professor Chang, for your kind introduction. Those of you who know me, Z. Zaworotko is hard for everybody. So if you ask questions, please say Dr. Z. So my lecture today will be all about crystals and why I consider them to be so important for the future of the world. And in the course of my lecture, I will tell you about GrACE, SALMA, and SAM. GrACE is my wife, by the way, but I'm not referring to my wife. I'm referring to green adsorbents. And Sam is my son, but I won't be referring to my son today. I'll be referring to switching adsorbent materials, which is also what SALMA addresses. Presently, I'm the Bernal Chair of Crystal Engineering and SFI Research Professor at the University of Limerick. This is our building on my opening slide, which is the new building of the Bernal Institute. And it's where my labs are based. So I would like to start with a bit of history. Why do we have a Bernal Institute? Well, Bernal is from this part of the world, in fact, this part of Ireland. And it's fair to say that J.D. Bernal is perhaps one of the most famous crystallographers ever, and one of the most influential scientists of the 20th century. One of his early papers reported the crystal structure of graphite, but more importantly, he reported the first ever X-ray diffraction pattern of a protein. And this was published in Nature in 1934. And I think it's fair to say that he started the field that we now call structural biology, and knew how important it was, if you see his comments about the diffraction patterns of proteins in 1934. Also on this paper is his student at the time, Dorothy Crowfoot, who later won a Nobel Prize, along with another one of his students, Max Perutz, who reported the crystal structure of hemoglobin. And of course, Watson and Crick. Watson was one of Perutz's students. So why are crystals important? Well, simply put, they matter to the real world. I've got 3 examples of crystals here. Everyone knows what the first one is, which is, of course, a diamond. The middle crystal is a molecular crystal. It's a pharmaceutical. And I think it's fair to say that the crystalline forms of pharmaceuticals are the most valuable materials in the world. This crystal, this image actually is a prize winner. It was called Starship Enterprise, and it won a prize in 2014 from the Science Foundation of Ireland as a scientific image. The right-hand picture is from my group, and it's also a prize winner. Just recently, it was given a prize by the British Association of Crystal Growth, and my student from China, Shiqiang Wang, won 2nd prize in the annual competition for crystals in art from the BACG, and he called this skyscrapers, which I think is entirely appropriate. So unfortunately, only 2 of these 3, I think, are of interest to me, but all crystals have the same properties in that, relatively speaking, compared to the alternative, they're stable, pure, have reproducible properties, can be processed, and my biggest interest is that crystalline materials can have the property of porosity. And that's what most of my lecture will focus upon today. So I'm not a big friend of diamonds, but I love molecular crystals, especially pharmaceuticals, and porous crystals, especially my porous crystals. But the challenge we face in science is not how to make crystals, to make crystals with good properties. It's how to design them from first principles. And that's where the field of crystal engineering aims. And it started in the 1950s. One of the most famous scientists, another famous scientist of the 20th century, Richard Feynman, gave a physics lecture which many people regard as the series of the beginning of nanoscience. And he has a famous quote, "There's plenty of room at the bottom," which is really a challenge for chemists to work up from atoms and molecules to build architectures and structures with properties, with better properties than what we had before. And Feynman issued a challenge. What would the properties of materials be if we could really arrange the atoms the way we want them? And he gave, I think, a very profound and important answer. He told us what you would be able to do, and that is you will get an enormously greater range of possible properties that substances can have and of different things that we can do. And that's the dream of crystal engineering. Essentially, design comes before properties, is the vision of crystal engineering. In the 1960s, the first example of practice or implementation of crystal engineering occurred. And the concept of what's called the topochemical principle and the 4 phases of crystal engineering were introduced by the group of GMJ Schmidt in Israel. Essentially, he said that in order to understand properties, you need to understand crystal packing. The same message really from Feynman, and he defined 4 phases, specifically in the context of topochemistry. You first need to experimentally determine crystal structures and correlate with properties. That understanding of topochemistry, establish the limits through new experiments, develop empirical rules, and then you go to systematic studies to make new materials with better properties. His concept was solid-state photochemistry. Today, we can apply this concept in various areas that I'll be talking about shortly. Schmidt's group, by the way, had some very famous people in it, names that are well known today, such as Hirschfeld, Coppens, Bernstein, Lahav, and Zaworotko. I became involved when I was an assistant professor. That's me in the front row of this conference in 1996, which was the first ever international meeting devoted to the subject of crystal engineering. It also led to our logo. And the logo, by the way, came from Sahari Kroto, the discoverer of C60. And this is our crystal engineering logo. Also, a book came out of this conference that was co-organized by my deceased colleague, Ken Seddon, who sadly passed away in 2018. I wanted to mention something briefly here because it will be relevant when I conclude and give you my take-home messages. There are some very famous theoretical chemists in this group, in this conference. This is Buckingham of the Buckingham Potentials, James Stewart of semi-empirical fame, and Bill Jorgensen of ab initio fame. From the very beginning, the need to merge theoretical chemistry with crystal engineering was obvious to us. And it's even more obvious today that molecular simulations and calculations can help us to design the next generation of materials. So where are we today? The definition of crystal engineering has to change because it's no longer just the design of crystals, it's also the properties and even more the applications of crystals. So crystal engineering is the field of chemistry that studies the design, properties, and applications of crystals. And if you're interested in applications, why not go for the world's most important applications, what many people call global challenges. And what I've addressed on this slide is that there are 4 global challenges that we actually, I'm sure, all recognize that can only be solved if we can do different things with new materials. So to me, these are the global challenges for materials science and engineering. Make solar energy more economical by making better light harvesting materials. Develop carbon capture, more energy efficient on use of sequestration methods. Find better ways to purify and provide clean water. And also to engineer, and I would say not just engineer better, but also cheaper medicines. The problem is that we somehow have not been able to solve these challenges despite 20 to 30 years of effort in these areas. I have a partial explanation for that, and it's because we tend to divide research into pure and applied. Pure, some people would call that bore research. That's not me, that's other people who would call it bore research, and that's pure scientific knowledge for the sake of science, which we need, but which is not going to solve today's problems right away. Industry tends to focus on what could be called Edison research, where the goal is not scientific knowledge, but new technology. But the quadrant that we really want to be in is so-called Pasteur research. And Pasteur research is targeted research. It's not basic or applied. It's a combination. It's a combination of developing new scientific knowledge with the goal in mind from the beginning of addressing technology. Of course, there's a fourth quadrant, which I never used to have a name for, but anybody who's interested can look up about this. Theranos is a company that spent $1 billion with no science and ended up with no technology. And it's created quite a scandal in the United States. So let's talk about quickly pharmaceuticals before I move on to porous materials. At the University of Limerick, we house the National Centre for Pharmaceutical Research. It's called the SSPC. I'm one of the co-directors along with Professor Gavin Walker, and Dr. Denise Croker is the executive director. It's a consortium of universities and companies in Ireland, and it has a budget on the order of around about 10 million euros a year. So it's a large center based in several universities, and it has more than 100 researchers associated with it. What we do in SSPC, in the current version, which we call Farm 5, is we merge groups in 5 themes to address industrial challenges. So the science is in modeling new molecules, formulation of medicines, the materials properties of the components of the medicines, and how you manufacture them. But the challenges that we're addressing came from industry. So industry told us what the problems were, and this is how we go about solving them. And our objectives are to link with both manufacturing, especially in Ireland. Ireland is one of the world centers for pharmaceutical manufacturing, but also to engage with companies around the world, especially the corporate R&D. So let's go back to the challenge, better and cheaper medicines. How do we go about that? And for a bit of context, the pharmaceutical industry worldwide is worth around $1 trillion, or around 1.25% of world GDP. And I think everybody knows that pharmaceutical products or medicines come from molecules, normally small molecules. Nowadays, there are biological molecules in this mix too. What not everybody is so aware of is that there's a big important part in the middle of turning a molecule into a medicine. And that is the so-called materials stage of drug discovery and development. And this is where the active ingredient and other components are brought together in order to make the drug product actually work. And there's an awful lot of research, an awful lot of value in this part of pharmaceutical science. And the problem we have in this area is that the molecule's molecular properties might not lead crystal material. That's the right property material. And 2 properties are important. Solubility. If a compound is not soluble, it will not be absorbed by the body. And also stability. If a molecule is not stable to humidity and normal everyday environment, then it's not going to be of any use for use in a drug product. So the materials properties in here are key to the performance of a drug product. What we work on is a field called cocrystals. Cocrystals, which are basically combinations of compounds, molecules or ionic compounds, but are multi-component. Molecular cocrystals have been around since at least 1841. Organic chemists will be familiar with the compound quinhydrone, which is hydroxyquinone and paraquinone, a cocrystal of the 2 molecules. They fall under the general category of molecular crystals, where there are 2 or more different neutral compounds that come together normally through halogen or hydrogen bonds, to form a new crystalline solid, which has two stoichiometric amounts of two molecules. Ionic cocrystals date to even earlier than molecular crystals. Sodium chloride and urea, if you dissolve them in an equal ratio in water and evaporate, you won't get sodium chloride and urea separate. You'll actually get a cocrystal of sodium chloride and urea. And we prefer ionic cocrystals because you have two variables. You have a target compound plus a cation, anion, and/or molecule. So there are three components in an ionic cocrystal. They're also held together by charge-assisted hydrogen bonds or coordination bonds, which are stronger than halogen or hydrogen bonds, so therefore tend to survive in water and change the properties more dramatically. Why cocrystals are quite different from single component crystals is that they can be designed from first principles. So cocrystals 201 is the complementary hydrogen bond patterns can be used to design new cocrystals. This is actually the cocrystal of quinhydrone that I just mentioned. And this is another famous cocrystal. This is a base pairing from DNA, the AT or adenine thymine complex, in this case based upon methyl adenine and methyl thymine. And the key to these cocrystals is the hydrogen bonding patterns that can be recognized and then used to make related but different cocrystals. And the field of cocrystals has increased quite dramatically since 2003, which is when the first pharmaceutical cocrystals were proposed and presented and published. And what you've seen is a steady increase. There's now more than a paper a day, and the number of citations is also going up quite dramatically. That's the red line. Now, those of you who work in moths will know that the y-axis is very different. I shouldn't say the x-axis is different. The y-axis is very different in the moth field. There's at least 10 times more citations and 10 times more publications. But this is still quite impressive by most standards. And the reason we study cocrystals is very simple. They work. They can dramatically change the solubility of organic compounds and therefore lead to enhanced bioavailability. And here you see two examples of natural products, quercetin and naringenin, which in their co-crystals have a much higher bioavailability. And by the way, this work is a collaboration with the Lu Tongbu group, who is at Tianjin University of Technology. So I did mention in the beginning, I've been to Tianjin many times, and I have many reasons to go back again. This is one of those reasons. What do these plots show? They show availability improvement. They show the bioavailability caused by cocrystals. Quercetin is extreme. Quercetin itself is very low solubility. That's the red line, and there's essentially no bioavailability. Several of the co-crystals of quercetin dramatically improve the solubility and dramatically improve the bioavailability of quercetin. So to conclude on co-crystals, they can dramatically improve the properties of a molecule without changing their chemical structure. That means that you have the potential to make better medicines, but also cheaper medicines, because you can take old molecules that have the wrong physicochemical properties and make them work. So what I like to say is that co-crystals represent, by the way, I'm checking my WeChat to make sure that everything's okay, because I'm assuming somebody will contact me by WeChat if my sound goes or my video goes. So Every now and then I'll check my WeChat. You'll be pleased to know I like to use WeChat a lot. So in terms of cocrystals, they offer improvement, control over physicochemical properties, new patent opportunities, no change in structure. 505(b)(2) in America is a fast-track way to approve new drug products. And in fact, the FDA in the United States has strongly endorsed cocrystals for use in drug products. But there are still some challenges with cocrystals that I've highlighted in red. So let's move on to the porous materials. Challenges 2 and 3 are related to gases and vapors, in particular commodities that are used in the chemical and petrochemical industries. And for a bit of context on the chemical industry, it's a much bigger industry than the pharmaceutical industry. It's over 5 trillion a year, which is around 7% of world GDP. And the reason the gases and vapors are important is that we're now in the age of gas, where coal is gone, oil is on the way out, but natural gas is the starting point, or the energy that we use in terms of production of commodities. And the chemical industry has a huge energy footprint, and a large part of that is because of the energy cost of separations and purification. If you have to distill something in a huge tower, a lot of energy is used. And at this point in time, around 10% of all the energy in the world is used to support the chemical industry, mainly for purification and storage of gases and vapors. And this could triple by 2050 if the world's economy keeps growing as projected. Of course, natural gas is also projected and is used as a fuel for transportation. CO2 is a gas, and it's a problem because it's everywhere, and we don't want it to be everywhere. And last and definitely not least, water is perhaps the biggest challenge we're facing because of the global shortages, which actually include northern China, which is short of water. And water capture, purification, and dehumidification also use around 10% of global energy. So the solution that I and others are proposing is that physosorbents can dramatically reduce the energy footprint for gas and vapor purification by avoiding the use of chemical methods or methods such as distillation. So solvent extraction, distillation, and chemical reaction all require a lot of energy. Physosorbents, if they work, could potentially reduce the energy footprint by up to 90% of separations. The problem is that if it were easy, we'd have already done it. Breaking up similar molecules that are in a mixture is not as easy as we would. Sorption 101 is to realize of separation or adsorbent. One of them is physosorption, which by nature uses weak forces, non-covalent forces, but has advantages. It's easy to recycle, it's typically fast, and the energy is not that high to recycle the material. The problem is that for the same reasons, the selectivity tends to be low. Chemisorption is the opposite. What we really want is to find adsorbents, physosorbents, that are very strong, but not as strong as chemisorbents. So a sweet spot of energy, which is in the 45 to 60 kilojoules per mole range. And the approach that we and many others are using is to build coordination networks. They're highly amenable to design. To me, paper number 1 in this field, before it was MOS, was published by Richard Robson, two papers actually, JAX in 1989 and ChemCom in 1990. This is the ChemCom paper, which is a simple coordination network, a two-dimensional coordination network that introduced the design principle of node, which is the metal, plus linker, which is the organic molecule, which links the metal centers, resulting in a nanoscale cavity, which is the key to building porous materials from first principles. So this is the concept that was introduced over 30 years ago now, and the end result, I'm underestimating this, but there are tens of thousands of distinct network structures that are porous or potentially porous. And the number one ligand in all of those, by the way, is the ligand that was used in the first SQL network, which is 4,4' bipyridine. So then that brings us to adsorption 201. If we can control the structure, what do we want it to do? Well, adsorbents can be classified by pore size. And what we know now, which we didn't know, I wish I'd known in the beginning, but I now know for sure, is that ultramicropores are going to give you stronger sorbent-sorbate interactions. And it should be obvious, because if you have a pore size that matches the sorbent and the sorbate, then the sorbate will see interactions on all sides and will have a much stronger interaction than microporous or mesoporous structures. The moment when we figured this out happened in 2012, when we studied a known compound, zinc, where pyrazine is the linker, and hexafluorosilicate, an inorganic anion, is also a linker, and the material CYP6-3 zinc was studied in terms of adsorption for the first time. And my undergraduate students at the time, Stephen, Amanda, and Amy, came back with an amazing isotherm of CYP6-3 zinc, which showed that at room temperature, that it was fully loaded very early at low partial pressure, unlike any other adsorbent at the time. We now know why, but before I go to that, I want to talk a little bit about pore chemistry. So if we can control the structure, we can control what goes into it, then we can control the pore chemistry. And the pore chemistry is really equally as important as the pore size. This is CYP6-3 zinc in the middle. A very famous MOF, DMOF1, which is a very large family of MOFs, has the same basic structure as CYP6-3 zinc in terms of topology and pore size even. They're quite similar, but the pore chemistry is very different. CYP6-3 zinc is inorganic lining, DMOF1 is organic. There are also purely inorganic analogs, and we shouldn't leave Prussian blue out of it, because really the protein is this type. For these new generation porous materials, the so-called hybrids, HUMs, such as CYP6-3 zinc, and MOFs, such as DMOF1. Prussian blue is important, but it's also famous. It's the first ever manufactured material because it was used as a pigment, a synthetic pigment. And one of the most famous paintings in the world, by most people's measure, is from Van Gogh. The dark blue in Starry Night is Prussian blue. And another famous painting, this time from Japan, The Great Wave of Kanagawa, also has dark blue. And guess what? It doesn't lose its color over decades, over even hundreds of years. So Prussian blue is a good template and a good model for a material to study. And there is a long story there because Prussian blue is porous also. So let's move then to the GrACE, SALMA, and SAM to explain what I mean by those terms. Green Adsorbents for Clean Energy, or GrACE, is the project that's been funded by the Science Foundation of Ireland to look at ultra-microporous materials. And what we've ended up, thanks to GrACE, is several new records for selectivity, and not just for CO2. CIF63 zinc set a new benchmark for CO2 nitrogen and also CO2 methane. New generation versions of CIF63 zinc are a further order of magnitude better. A different hum that we call CIF62 copper I set a new record for acetylene ethylene selectivity, which also has been significantly improved since. And this was a science paper published in collaboration with Banglin Chen in 2016. And most recently, we discovered a material, again, a known material, an azolate material. So we call it the Generation 1 azolate ultramicroporous material, which showed what some people would think is inverse selectivity. That is that ethane was preferred to ethene. Normally, it's the other way around. Most sorbents prefer ethylene over ethane. So GrACE was basically aimed at discovering new ultramicroporous sorbents with new record selectivities for given pairs of gases. What all of this does, when you start adding it up, is creating a new approach to separations, which is that when you're dealing with complex mixtures, and the world's largest industrial process, by the way, is ethylene production. So this is the example I have here. Instead of a three-step process, each of which is energy intensive, now if you have a customized sorbent, you can remove each of the impurities in sequence. So you can start with a complex mixture, pass it through a series of sorbents, and end up with a purified gas at the other end. And this was our 2019 paper. Another Chen, Kaijia Chen, who was in my group at the time this work was done, but is now at Northwestern Polytechnic University in China. And what he showed is that by indeed combining three sorbents, it was possible to take a complex gas mixture and in one step, with essentially very little energy put into the system, produced clean ethylene, polymer-grade ethylene at the other side. So this was published in 2019, and in 2020, I was fortunate enough to be awarded an ERC grant to further pursue this work. So what did we learn from this? What we learned is that we have design principles. Remember that we designed the material, so we controlled what went into the material. So the key design principles are narrow pores and inorganic walls together can lead to strong interactions and benchmark selectivities. The reason is that we're creating a binding interaction that's highly selective because of both the pore size and the pore chemistry. You also can get a high density of these binding sites to give you good working capacity. And this is quite important. There's only one binding site. So there's uniform or close to uniform energy across full loading, which is never the case for larger pore materials, where sorbate binding starts taking over after the pore walls are covered. What we didn't know at the time, in fact, people were telling us, you're going to fail because kinetics will be bad, is that the kinetics is actually much better than well-known materials such as zeolite 13X and magnesium MOF 74. Here you see CO2 loading to an empty material, time versus full loading. And the hum materials, the ultramicroporous materials, are actually much faster than the wider pore materials. So at this point, we have a very good situation. We can now clean up gas mixtures, not just binary gases. But there is a big problem that everybody tends to ignore, which is that water vapor can really mess up your adsorbents. It can also co-adsorb, and then it reduces or overwhelms the amount of CO2. And we knew this back in 2015, 2017. So much of what we do now is focused upon controlling water absorption in both directions and perhaps exploiting it. In terms of controlling it, also in 2019, my group published a paper on CIF618, which is telling you how far these materials have advanced from CIF6-3. We're actually up to 23 now, I believe, CIF6-23. And this had a very unusual binding site, which was CO2 philic and hydrophobic. So this was published in Science Advances. So we're making progress on the binding site side. We're also making progress on the water harvesting, water capture, water purification side. And I mentioned earlier, I consider this to be the single biggest challenge facing the world or facing materials science. Simply put, there's not enough fresh water and the prospects are grim. So most of the world, or most of the people in the world, 2 in 3, live in a country that's facing a water crisis, an imminent water crisis. And already 4 billion people don't have regular access to clean water. And things are getting worse. 95% of humanity lives where there's less water now than 20 years ago. I mentioned China early on. The northern half of China is water short. But it's not as bad as some other parts of the world, which are in even worse shape. India is in much worse shape than China. Even Europe has issues. Ireland does not. Ireland is the little green island at the extremity of Europe. And water is also important for agriculture and industry. The water shortage is not just going to affect domestic use, but also hugely affect agriculture and industrial use. So most people are familiar with fresh water. There's quite a lot of it. But in fact, only about 0.3% of it is clean. 31% of groundwater is not suitable for drinking. A lot of it is trapped also in ice, glaciers, and snow. And only 0.04% is in the atmosphere. Now, that might not sound like a lot of water, but in fact, it's an enormous quantity of water. At any one time, there's over 10 to the 16 liters of water in the atmosphere. So this is actually a renewable source, and it's clean. It's naturally clean. All we have to do is find a way to capture it economically. And zeolites, of course, are used as dehydrating agents and will capture water from the atmosphere, but, and they're used as desiccants, but they use too much energy. They use much too much energy for recycling. So what we need to do is discover a new type of absorption, of water absorption, which is either a weak so-called type 1 isotherm, which is the green line, and also a type 5 isotherm where the threshold is below low humidity. So to cut a long story short, we need something that really wasn't that common if it existed at all. We don't want it to be too strong. We don't want it to be too weak. We want it to be just right in terms of water absorption. And when we can discover adsorbents like this that are economically feasible, then we have the potential to address water harvesting through good working capacity, low energy to recycle the material, and fast kinetics of the sorption process. And when we started this work, just around 2 years ago, we had no prejudice. We didn't know in advance where to go because there wasn't that much information out there in the literature. So we considered something old, zeolite 13X, something new, hum materials, something borrowed. Moth 801 is one of the materials touted by Omoyagi's group for water harvesting, and something blue, which is a material that an old moth that my group had made and reported in the literature previously. And what you've seen from these slides, or should be able to see from this slide, is that this Rust 37 material has the type of isotherm I was talking about earlier, because it takes up water and fully loads at around 10% humidity, which is lower than any humidity on the planet, including the middle of the desert. And then we just simply screened these materials, the leading materials, by various sorption processes, and came up with rankings of materials. So we had performance number 1 would be the working capacity at 30%, relative humidity. And what you see here of the materials we studied, moths were the winners. The top 3 materials were all moths. For the kinetics of capture and release, we found that there were wide variations in performance, but one material, the green one in the middle here, was fast to load and fast to unload. And in fact, moths won this too. The best materials for kinetics were also moths. And also then we studied the heat required, and lo and behold, moths once again were the winners. I mentioned earlier that zeolites had an issue because of the energy. The amount of energy needed to remove water from most zeolites is extremely high. In this case, measured by temperature over 200 degrees C. Some of the moths we were studying were down at 40 or 50 degrees Celsius. And the winner at the end of the day, at least from our initial study, was this material, Rust 37. As you can see, it can be cycled very nicely for 30% water capture, and it has the right combination of features to move forward. But that doesn't mean we've solved the problem. Solving the problem means a lot more than just having good properties in the lab. All kinds of things have to be taken into account, including scale up and cost. The cost is clearly a critical factor. And we've collaborated or partnered with a company called Molecule to take what we discovered in the lab and start formulating it and scaling it up. And we're now able to produce composites of Rust 37 that can be used in water harvesting machines. So in a really, I think, a very short time, 2 years, less than 2 years, we've gone from not having a lead material to testing prototype water harvesting machines. If you add 2 and 2 together, and you can capture water and capture CO2, then our next project that we hope to push, which we call C-, is farming in the most arid regions of the world using water capture and CO2 capture. I'm going to conclude with a very brief introduction to what I think is the next stage of porous materials related to what I've just shown you, and we call them switching materials. Materials which switch suddenly from closed to open phases. Our first paper in this area was published in 2018. We published a number more since then. And the advantage of the switching materials is the type of isotherm they have. To cut the long story short, they give full delivery of what they capture if the switching event occurs at the right pressure and temperature. So the working capacity will always be better than equivalent rigid materials, but there are very few of them. And most of the flexible materials in the first generation were irreversible because their mechanism of capture and release required large structural changes. So this is where SALMA comes in, which is funded by the Irish Research Council, by the way. In our case, to get around the stress issue, we're looking at layered materials, which go from closed to open in a clay-like fashion. And our first example, published by my student Shicheng Wang, was one of the old, long-known two-dimensional coordination networks, SQL1CO NCS, we call it. And here you see it switching for CO2, and a very stable, recyclable material. Shicheng also studied the same material for xylenes separation and found that you get both high capacity and high selectivity for one of the most difficult separations around, which is separation of the C8 aromatics, the xylenes and ethylbenzene. Last, where do we go next? And we're just starting to look at what we're calling SAMs, which are switching adsorbent molecular materials. The prototypal material was actually reported in 1969. A simple variant of that was our first paper of 2020, which was a SAM material which was able to selectively capture orthoxylene. So to finish off, my take-home message is based upon really only the last 7 or 8 years of working in this particular area of the ultra-microporous materials and separations, is that the right pore size plus right pore chemistry is needed for strong selectivity. Even small changes in pore size and structure can lead to big changes in properties. Large changes lead to even larger changes, obviously. Predictive modeling, which I haven't emphasized today, is a key part of what we do. I believe it's within reach. I think we have enough now synergy between experiment and modeling to publish papers together. What's been a real unexpected pleasure is not just that we have good papers, but we have really good properties. And the properties that we're reporting are not just a little bit better than what was there before. In almost all cases, we were seeing order of magnitude or more than an order of magnitude improvements in properties. And I'm going to predict that the next wave we're going to see, if we can combine these properties with switching or sieving, is that these will be the next big focus for this field. So I'd like to acknowledge the people who did the work. We haven't had a Celtic 2020, that's my annual meeting, so I have no new pictures of the group, unfortunately, thanks to COVID. My group is multi-talented, diverse in culture and gender, and I'm very proud of that. I want to acknowledge, in fact, that I have several Chinese researchers in my group. This is Shicheng, BQ or Bao Qiao, as we know him, and CD or Chunghua Deng, who actually is in Tianjin right now. He was a student at Nankai and has been stranded by COVID, but we hope to have him back soon. I also want to acknowledge the fact that Brian Space is my main collaborator in the modeling. We have around 40 papers together. Without his modeling, we wouldn't have understood as well why our materials work so well and how to design the next ones. Finally, thank you for the opportunity. There's Professor Zhang for inviting me to speak to you today. These are some scenes of Limerick and close to Limerick. The coast close to Limerick is very beautiful. We have at least one thing in common. With Tianjin, the largest river in Ireland flows through Limerick. This time last year, I was in Tianjin, and I know very well the river in Tianjin because I've taken the boat ride every time I come. So thank you again for your attention. And hopefully the technology worked and we can answer some questions.
Okay. Thanks for from the live platforms for you to answer. Thanks for your time. Okay. So the audience asked one question. Is there any way to predict the solubility of crystal drugs? Yeah,
is there any way to what was the question again?
Yeah, is there any way to predict the solubility of crystal drugs, just as you mentioned in the slides?
I wish. So predict is a strong word, right? Expect. So English sometimes, no, not sometimes, can always be confusing. So predict means you have a certainty. Expect means you think that something will happen. And when a chemist looks at a molecule, they have a reasonable expectation that a molecule will be water soluble or not, right? Every chemist can look at a molecule and say, oh, it's got hydrophilic groups or hydrophobic groups. But predicting the magnitude is very difficult. And water solubility can range over enormous ranges from 10 to the minus 7, 10 to the minus 8, up to fully miscible, right? So you can expect, but you can't predict. And when it comes to pharmaceuticals, if a compound is 1 mg per mil instead of 0.1 mg per mil, that can have a big effect on the bioavailability. So the answer is you can calculate, you can expect, but I don't think even today, I don't think it's easy to know in advance what the precise water solubility will be of a compound. So our approach is to make lots of versions and hope that one of them is right. I'd like to say that we're smarter than that, but no, I don't think so. I'd be interested to discuss it if anybody would like to go there.
Okay, thanks, Mike. Another question is how to design materials with good separation performance. Ion and the ligand are important also. Yeah, this is a question from the audience.
Yes, everything is important. So I can go to my final slide, all my take-home messages on that, right? This is the hard part. You need the right pore size and the right pore chemistry. So by slight changes, so my first two take-home messages tell you that you can get roughly there because we know we need small pores and we know we need certain types of molecular recognition. Now, as it turns out, this particular slide shows the cover image from Chemistry European Journal. And this particular material has a different type of binding site than the ones we were looking at previously. This is halogen acetylene binding. So if you study supramolecular chemistry, you'll know that halogens can have some very interesting interactions. Halogen bonding is now becoming much more recognized and much more used. And here we had halogen acetylene bonding. So this material had a very different pore chemistry and binding site. So the challenge is to know whether it's fine-tunable and whether you can systematically change it. So I think we know some basic rules now for the key gases, but we're only at the beginning of this. There are still new types of binding site to be discovered, and there are improvements in performance still to come. It would be hard to believe that we're at the end of this story at this point in time. I wish I could be more specific, but I'll go to my first take-home message. The right pore size and the right pore chemistry, but we don't know what that is. We only have a rough idea. We have to do the experiments still.
Thanks for your response, Michael. And another question is how to solve the problem of HUMs between the low sorption capacity and the high selectivity. Yeah.
Well, the sorption capacity is not that low if you measure it by volumetric measurements. So if you go by gravimetric, then high density materials don't look good, right? And most of the literature in the MOF field uses gravimetric numbers. But if you actually go to volumetric, you'll find that many of the hum materials actually have better uptake volumetric than many well-known MOF, because their density is 1.5. So going back up to, so what is enough is the question. So let's go to this particular slide. What you see here is that the actual density of the binding sites is quite high. So the uptake of CO2 gravimetrically is much lower than, say, MOF 74, magnesium MOF 74. But volumetrically, they're much more similar. So my answer to that is focus on volumetric measurements, which ultimately, for most applications, are more relevant. Certainly for the water application, it's the volume of your container that matters, not the mass of the container. And I was going to look at another slide here. Okay. So working capacity, these are measured in cc's per cc. Cc's of water vapor per cc of material. And a very dense, narrow pore material was number 2. Number 1 is one of the low density MOFs. Number 2 is one of the high density materials. So going volumetric doesn't give you the same numbers. It favors denser materials more than gravimetric. So I don't consider the working capacities to be low. In fact, if you measure volumetric, they're strong. Not the best, but they're strong.
Okay, thank you. Another question is, do we think SSST technology will ever be commercially viable?
My answer is I hope so. Because so this is what we showed with ethylene, right? This was the ethylene story. My dream is this, right? Another gas mixture, which is air, that we remove water and CO2 from air, and we use it for agriculture, use it. And the answer to my question could go on forever, right? We could be asking the same question in 20 years. I think we'll know in much sooner than that. If these materials work, you will see them in commercial use quite soon. And my hope is that this will be the one that comes first. But that air will be our gas mixture, and we'll find ways for direct air capture of CO2 and of water vapor to make water harvesting, CO2 harvesting, and apply it worldwide. So that's my dream. And I don't think it's as far away as it might be if the fundamentals are there, because there's a need. There's an economic need and a social need to solve these problems. So somebody somewhere will make the material that solves this problem. It doesn't have to be me. But I am optimistic that SSST, which is not just ethylene, it's a general approach to purification of mixtures, will find utility. And I'm pretty much saying I think the biggest one is air. Now that's the gas mixture that we live with and we need to control, but removing impurities from air is not easy. So that's, I think, where it could go first.
Okay, thanks for your question. And continue with the last question. Are MOFs advanced enough to capture excess CO2 from the atmosphere? Just you mentioned CO2. Yeah.
Yeah. Well, there are MOFs which can be chemically modified, but they're slow. If it's a chemical reaction and the CO2 concentration is only 400 ppm, then the reaction will happen, but it's slow. So yes, there is a way to capture CO2 from air today. Liquid amines will capture CO2 from air, and modified MOFs which have amines in them grafted will capture CO2 from air. But I don't think they work as well as the materials we have at 400 ppm in terms of kinetics. So it's actually a battle between will it be chemical or will it be physical? But otherwise MOFs don't. I'm unaware of any MOFs which can compete for direct air capture. They just simply don't have the binding and the high density of binding sites needed to capture CO2 from air. They will work well for flue gas, by the way. Flue gas is maybe 25% CO2, but 400 ppm CO2 in the presence of water vapor is a different problem. So yes, this is a big challenge, and it's the one we'd want to solve, direct air capture. So all of the questions were very good, by the way. I should have pointed that out. They were all very appropriate and good questions.
Okay, thanks. Another question is, how much can computer modeling be used to predict the next important MOF? Yeah, thank you.
I think we're getting close. But the problem is, and I'll go back to my take-home message slide. From a lot of experience, I'm not the person who does the modeling, but from a lot of experience, computer modeling can get the structures very accurate, but is not so accurate on the energies. So density functional does not do that good a job on hydrogen bonding, for example. So we're dealing with the same thing here. We can get perfect structures from the modeling, but they're off on the energies, especially strong energies, which lead to induced polarization. So modeling has to advance as well. We need new force fields that work better, that are more accurate on the energies. So I think that's the challenge now, is accurately determine the energy of interactions as well as the structures. The electrostatics are not electrically structured. So that's my understanding of the field as it is today, but I'm not an expert in modeling. That's just my understanding of the field today.
Okay, thank you. Another question from the audience is, what features of pore chemistry are useful for gas sorption? Yeah.
Well, we're back to my first point again. And, you know, perhaps the best illustration is comparing Prussian blue, CIF63 zinc, and DMOF1. All of them have roughly the same pore size, but their adsorption properties are extremely different from each other for everything, because their pore chemistry is so different. The question is, how much of a difference do you need to make a big change in the properties? And what we're discovering in these hum materials is that even small changes, changing the metal from cobalt to nickel, can slightly change the pore size, changing the inorganic from silicon to titanium hexafluorosilicate, changes the electrostatics, and you can have an order of magnitude change in selectivity in a good direction or in a bad direction. So we're still learning. This is, to me, the fun part. We're no longer randomly studying. We're systematically changing the structure using crystal engineering and understanding how the properties change. And that helps the modeling, by the way. So the two questions go together. If you can control the structure and control the properties, then the modeling can be modified to fit and developed further to the point it will get predictable. So I'm hoping that it'll take 5 to 10 years for predictive modeling to become possible. Reliable, I should say, not possible. Reliable enough to be used.
Okay, thank you. And the last question, I think is long, yeah, very long. If we use the MOMs in the energy-related field, what do we think of the collapsed and usable MOS after many cycles? Is there any way to avoid the MOM secondary pollution, especially the metal ions? Thank you.
Well, I know there are people, puffs and moths and mums and hums are all competing with each other, right? The problem with puffs is I don't know how you're going to get the inorganics are needed to get the strong interactions, strong electrostatics. When it comes to stability, I really have one comment only. No open metal sites. If you have open metal sites, then you have, I think, very little hope of surviving water. I think open metal sites in general have much more problems with water stability and also will strongly bond to water. Once you go away from open metal sites, then the stabilities, well, I've got the right slide up because Prussian blue is stable for hundreds of years. That's what you want, right? You want a material that is, to all intents and purposes, practically indefinitely stable. And there's an example, Prussian blue. So the chemistry is part of this too. Some chemistry will not survive exposure to the atmosphere, others will. Most moths, especially those with open metal sites, are not going to be practically useful. Switching materials, I've sort of given my perspective on that. I think that 3D switching materials, it's going to be very difficult to find materials that can undergo dramatic structural changes and undergo thousands or tens of thousands of cycles of absorption and desorption. So I think you pick your battles. You choose what goes into your moth, and you choose it to exclude open metal sites and exclude structures which must have dramatic structural changes and distortion in order to undergo recycling.
Okay, thank you. The last question is there any way to predict flexible materials behavior? Yeah.
I wish. That's the best question of all, right? Because it's not just,
Thank you.
there are people who are looking at these and trying to model in the gate opening, right? But it's not just that. It's not just gate opening. You have to know the structure of the open material. And then you have to know if it'll undergo co-adsorption or not. So co-adsorption is extremely challenging to predict. You can calculate selectivity, but it doesn't always work out in the real world, right? Because the less selective compound might be faster kinetically. So it's nowhere near as easy. Now it's even harder. Let's just put it that way. I'm not going to say any modeling is easy, but predicting a flexible material in terms of its gate opening, and in terms of whether it will selectively bind gas, and in terms of whether there'll be kinetics that are suitable in its favor, I don't think that's even possible at this stage. That's too hard. So we're back to empirical measurements, experimental work. I wish is my answer.
Okay. Hi, Mike. Thanks for your response to all questions. Yeah, and thanks again for your time. And
Thank you.
welcome to submit your work to SmartMath. Yeah, in future.
You've reminded me. Everybody's reminding me. Yes, I plan to submit two.
Yeah, thank you.
An original article.
Thank you.
Yeah. And I think that one of them will be on a flexible material. So I think that to me fits the theme of SmartMath, by the way. I think flexible materials, I think, are part of the future of separations, and SmartMath is a good place. The theme of the journal is good for that.
Okay, thanks for your support, and welcome to visit Tianjin City again in future when you are available, when the epidemic is well controlled in future. Thank you.
Yes, thank you so much. I enjoy every visit to Tianjin, but I don't like stinky tofu. So just in case all of you in Tianjin know what I'm referring to.
Yeah.
I love Chinese food, but stinky tofu is too much for me.
Yeah, thanks. Just like you also mentioned, gobli is delicious. So
yes.
yeah. Thank you.
Gobli very good. Stinky tofu not so good.
Yeah, very famous.
Okay, Mike, thank you. Thank you for your nice talk.
Yeah, thanks for your nice talk. Yeah.
Thank you. My first ever virtual lecture. So number one.
Very good. Very good.
Thank you.
And also look forward to see you in the near future in Tianjin or in Hong Kong.
Yeah, I was in Hong Kong not that long ago too. Yeah.
Right. Okay. Zhicheng can link us up by the WeChat.
Okay. Yeah. Later I will transfer the WeChat to you. Okay. Thank you.
Okay.
Thank you, Michael.
Yeah. Okay. Thanks
you for your talk.
Bye. Take care. Bye.
Yeah. Bye.
Bye, everyone.
Yeah. Bye.
Bye.
Yeah. And finally, I'd like to thank the organizer Research Cloud, in Chinese, for the kind support, and also. Yes, thank you the audience for your attention. And at 9 morning a.m., Professor Federico Rossi from Institute of National Dina Research Scientific will give a talk on multifunctional materials for emerging technologies. Welcome to listen to the talk. Thanks for listening. See you tomorrow morning. Thank you. Hi, Michael. Thank you. Thanks again.
Thank you. Bye-bye.
Bye-bye.
Bye-bye.